This is the last video of categorical analysis, video 6. We'll discuss about 3 effective measures here: risk difference, risk ratio, and odds ratio. Suppose a study is conducted to investigate long-term complication rates in patients treated with 2 different therapies. In the table, we see among 89 plus 127 total patients with therapy 1, 89 of them experienced a complication and 129 does not. Among 873 plus 911 patients with therapy 0, 873 experienced the complication and 911 did not. The second table is the same table, same 2x2 table with general notation using A, B, C, D instead of the actual number. The risk itself can be calculated for each group, therapy 1 and 0. The risk of the therapy 1 group, the risk of the complication is 89 divided by 89 plus 127. Which is 0.412. The risk of the therapy 0 group, the risk of the complication is 873 divided by 873 plus 911, which is 0.489. The complication risk is higher for therapy 0 group. Here we are using 0 for our subscript for the second group, since the second group often is a control group. For other cases, we can use subscript 2 instead representing group 2. The first effect measure, the risk difference, is the difference between the 2 risks. In this example, the risk difference is 0.412 minus 0.487, which is negative 0.077. This is smaller than 0, since the risk is higher in the group 0. When the risk difference is less than 0, group 0 has the higher risk. If the risk difference is larger than 0, group 1 has a higher risk. The relative risk is the ratio of 2 risks. In this example, the relative risk is 0.412 divided by 0.489, which is 0.8425. If it's smaller than 1, we're comparing to 1, and this means group 0 has a higher risk. When the relative risk is larger than 1, group 1 has a higher risk, and here group 0 has a higher risk. Odds ratio is another popular effect measure. As the name implies, odds ratio is a ratio of the odds, and odds is defined P over 1 minus P. Odds ratio is defined the ratio of 2 odds with different probability. Okay, like this. In this example, the odds ratio is 0.412, which is our first P, the risk, divided by 1 minus 0.412. So the numerator is the odds of the first group. And then 0.489 divided by 1 minus 0.489, which is the odds of the second group. So our odds ratio is 0.7438. The odds ratio is less than 1, and this means the complication odds are higher for the group 0. We can also say those who have the therapy 1 is 0.74 times more likely to have the complication than those who have therapy 0. Or therapy 0 has 26% less times of complication. No more times complication than therapy 1. In 1973, UC Berkeley was sued for sex discrimination. Out of all female students who applied, only 35% of them was admitted, while 44% of male male application were admitted. This difference was concerned, and UC Berkeley set out to find the main culprits of this gender discrimination. To do this, they broke up the data to see which departments were mainly responsible for the gender bias. The data from the 6 largest department is listed below. After breaking up the data, we see a different story. Out of 6 departments, 4 of the department, here, and here, accepted women more than men. There was a gender difference, but it was in favor for the woman, not against. So why did the aggregated data tell a different story? This is a classic case of Simpson's paradox, when grouped up data tells the opposite story of the ungrouped data. This happens because of the confounding factor that is hidden from the site within the data. So what's this hidden factor that's causing all this mischief? Take a look at the first and the last row of the column. So Department A and Department F, we're going to look at. You'll notice that Department A has a pretty high acceptance rate. High acceptance rate, especially for women at 82%. Okay. However, out of 4,000 plus women, only 108 of them applied to Department A. That's only 2% of all women who applied across departments. On the other hand, 825 of men applied to Department A. That's 10% of all the male applicants. Now, take a look at the last row. Again, woman has a higher acceptance rate than the man, which is 6%. But over here, Department F is, in contrast to Department A, has a very low acceptance rate. Compared to men, a much larger portion of women apply to the lower acceptance department. Around 4% of all male applied here, while 8% of all women applied to the Department F. So in truth, women weren't being discriminated against. It just so happened that a large proportion of them were applying to the low acceptance rate department, while a large proportion of men were applying to the high acceptance rate department. That skewed the overall results. And this is actually very classic Simpson's paradox example.